We have seen already that when we connect a capacitor to the terminals of a power supply or a battery, a current will flow in the circuit for a short time as the capacitor charges. Charge accumulates on the plates of the capacitor. One plate of the capacitor becomes positively charged, the other plate of the capacitor becomes negatively charged, and as that occurs, the capacitor will store electrical potential energy. We have seen that, and we can see that here in the circuit, where we connect a capacitor across the terminals of a power supply and then disconnect it from the power supply and connect it to the filament lamp here. What we can see is that briefly the filament lamp will light. This is occurring because the electrical energy that has been stored by the capacitor when it charged from the power supply is then dissipated across the filament lamp, causing it briefly to flash as the current flows through it from the capacitor, in order to discharge the plates of the capacitor. If we consider the capacitor charging circuit shown here, what will happen is that a current will flow briefly from the power supply through the resistor while the capacitor charges. So here we have the positive terminal of the power supply, here we have the negative terminal of the power supply. And that will mean a conventional current flowing in this direction, and therefore we have electrons flowing the opposite way around the circuit. Electrons flow from the negative terminal of the power supply through the resistor onto this plate of the capacitor, which becomes negatively charged. This plate will acquire a positive charge whilst the capacitor is charging. While a current is flowing in the circuit, negative charge, negative electrons are flowing onto this plate of the capacitor that you can see here on the right, and at the same time negative electrons are flowing off the other plate of the capacitor around towards the positive terminal of the power supply, and we're charging the capacitor. We've already seen that charge is equal to capacitance times potential difference across the capacitor. So the charge stored on the capacitor can be calculated by its capacitance multiplied by the potential difference across the capacitor, which we can measure here using the voltmeter. So if we plot a graph of potential difference against charge here, what we can see is we have a straight line graph here. We know that Q equals CV. If I rearrange that, V would equal 1 over C times charge. Compare that to the form Y equals mx plus C for a straight line. If I plot V on the y-axis, the vertical axis, charge on the horizontal axis, we would have a graph here, the gradient of which would be 1 over the capacitance. Now what this also shows us is that as the capacitor charges here, because the potential difference across the capacitor increases, it becomes harder to add charge to the capacitor. If you think about it, basically as electrons begin to flow around here, the capacitor begins to acquire a negative charge, which repels the incoming electrons here, and so it becomes harder to push more electrons onto the capacitor as it charges. Now we know that the definition of potential difference is potential difference equals work done over charge, or in other words, work done equals the charge multiplied by the potential difference. If we add a small amount of charge, delta Q, to the capacitor, then provided it's a very small amount of charge, the potential difference will increase very little as we add that charge to the capacitor. And if it's a small enough amount of charge, really the potential difference won't increase to any significant amount, so we can assume the potential difference would be constant. If the potential difference is constant while we're adding this charge, then according to the formula here, the work done would just be the charge multiplied by charge delta Q multiplied by the potential difference here, which in my example is V1. In other words, what we would be doing is working out the area here of what would be a rectangle. Provided that strip is small, it's narrow, we're only adding a very small amount of charge, what we will do here is to work out, to determine the work done, charging the capacitor here, adding this charge delta Q to the capacitor. What would the work done adding that charge delta Q? It's just delta Q V1. Now if I wanted to work out the total energy stored then in charging the capacitor, the total work done charging that capacitor, the amount of electrical energy that capacitor stores. What I would have to do then is work out all the area of all these different strips here. So let's say we had another amount of charge delta Q here to the capacitor. We could put that in here, and let's say if it was a small strip, again the potential difference would be constant. We could call that potential difference V2. We could work out the area of that rectangle and all of the other rectangles here that would be under this line. In other words, what we would have ended up doing here is determining the area under the graph. So the area under the graph here is the work done charging the capacitor. Now obviously this is a triangle, so if we charge the capacitor all the way up to a potential difference V, by which point we've got a charge stored on it Q, the energy stored on a charged capacitor equals half QV, where Q is the charge stored on the capacitor, so that's the positive charge on one plate, the negative charge on the other plate, multiplied by the potential difference that you measure across the capacitor once it is fully charged, half QV. Now we can write in a couple of other formula then, because of course we know that Q equals CV. So if I replace Q with CV, what have we got? We've got half CV squared. C is the capacitance, V is the potential difference across the capacitor. So there we are, we've got one formula for the energy stored, we've got a second formula. What we could also do is replace V here with Q over C. Rearranging that formula, V equals Q over C. So if we replace V here with Q over C, what we've also got is half Q times Q over C, which would be Q squared over 2C. So the energy stored on a charged capacitor is equal to half QV, which is equal to half CV squared, which is equal to Q squared over 2C. So you can use any of those formula to work out the energy stored on the capacitor once it is charged, depending on whether you know the charge and the potential difference, capacitance and potential difference, or charge and capacitance. And there we go. One thing to realise is, okay, once you've charged the capacitor up to a potential difference V, the energy stored on it is half QV, but the work done by the power supply to move that charge, a total charge Q, around the circuit here, okay, in total the charge Q has moved round from the one terminal of the battery to the other terminal, and so the work done by the power supply is still QV. Okay, the power supply here with an EMF E, basically if you multiply that EMF by the charge that's moved from one terminal to another, that's the work done by the power supply, but the capacitor has only stored half QV. Where is the rest of the energy gone? Well, it's been dissipated in the circuit resistances. This circuit, at least it will have an internal resistance. Usually it'll have an external resistance as well. And don't forget, when a charge flows, when a current flows through a circuit, there will be some resistance heating. Energy will be dissipated in those circuit resistances. So it works out that you've got an energy half QV at the end stored in the capacitor, and also half QV will have been dissipated in the circuit resistances whilst the capacitor charges. Once it's charged completely fully, there's now no volts across the capacitor, across the resistor. No more current is flowing in the circuit, but whilst it was charging, while the current was flowing, then energy would have been dissipated. There would have been heating in this circuit resistance, and that's again one thing that we need to appreciate. Okay, well here we have a question on energy stored in a capacitor. Similar to what we did in the first lesson where we charged a capacitor using a constant current. Very similar experiment. So here we had a 47 microfarad capacitor. We've charged it using a constant current. So to keep the current constant, what you would have to do, as we did before, reduce the resistance in order that as the PD across the capacitor rises and the PD across the resistance falls, then the current remains the same. So obviously a smaller PD across the circuit resistance, if you reduce the circuit resistance, you can keep the current the same. So that's what they've done. And they want us to know, well, in that situation, how much energy will be stored on the capacitor. Well, we know it's looking in our data book, we can look at the formula. So we already know, we talked about energy stored on a charged capacitor is a half QV, or half CV squared, or even Q squared over 2C. Well, we know the capacitance, which is useful, okay, but we also need to know either the potential difference across the capacitor or the charge stored on the capacitor. Now, we don't know either of those things at the moment, but we do know we've had a constant current of 62 microamps for 52 seconds. So what we can say here is we know that current, rate of flow of charge, so charge would be current multiplied by time. So if we have a constant current, if the current doesn't change over those 52 seconds, we can work out the charge. So 62 microamps multiplied by 52 seconds. That would be 3,224 microcoulombs. So at that point then we know what the capacitance of our capacitor is. And well, we've just worked out the charge stored on it, so we can use this formula, can't we, here? So let's write that down. And there we are, and we've got an answer of 0.11 joules. Don't forget, when you enter the numbers here, don't forget the microcoulombs times 10 to the minus 6, so we need to enter the prefix here, and of course microfarads again times 10 to the minus 6 on the bottom. And if you work it out, you've got 0.11 joules. So I've written the answer to two significant figures because obviously the data in the question here has been provided to two significant figures.